The topic of today is dealing with power related to the FX100 audio analyzer. Well, when we talk about power, we usually think of two applications. First of all, measuring the dissipated power across the load. And second, we may enforce a certain power dissipation in the load by adjusting the output of the amplifier, for instance, accordingly. So these two applications are both covered by the FX100 audio analyzer, and we will explain them to you and how to use them in this webinar. My name is Markus Becker, and I'm assisted today by Greg Schmiedle, our product manager for the Flexus line. He will mainly take care of your questions during the presentation. The topics that we have prepared for you start with an overview of the content of this webinar, followed by a view of the test configuration, and then we will enter the practical presentation, which is actually the major part of today's presentation. We will wrap up what we have shown to you in a summary section, followed by some hints and tips, and at the end we will come back to your questions and provide the corresponding answers. The overall duration of today's presentation will be in the range of about half an hour. So let us take a closer look on these typical applications that we support by the FX100. The first of all is to adjust the amplifier output level in a way that the power dissipation in the load reaches a certain predefined value. For this purpose, we need to know two parameters. We need to know the gain of the amplifier and the impedance of the load. And by knowing these two values, we can calculate the output level of the FX100 to generate the required power dissipation across the load. And this calculation is done absolutely automatically within the FX100, so you don't have to care about that. The second application is to measure the actual power dissipation across the device under test. This could be, for instance, the power dissipation at a specific frequency, or plotting it versus the frequency band, measuring the distortions expressed in watt versus frequency, or plotting the distortions versus the output power. And the setup here is principally the same, but the difference now is that we only need to know the impedance of our load, and then we can measure the level, the voltage across that load, and by that calculate the dissipated power. So in practice, it looks like that. We have our Flexus analyzer. We connect it to our amplifier. This feedback line is basically required to measure, for instance, the gain of the amplifier, or of course also to measure the voltage across the load here. And the load in our case is 4 ohm here in our practical presentation. The formulas that are applied for these calculations is this one. That's the one for the adjustment of the amplifier output power. So here in red you see the output voltage of our generator of the FX100. That is the value we have to calculate, and for that purpose we need to know the gain of the amplifier and the load impedance, and of course the designated output power of our amplifier. The other formula, the measuring formula of the dissipated power across the load, is basically the same. We measure the voltage across the load, square it, divided by the load impedance, and that gives us the surge value, the dissipated power that we want to know. Once again, these calculations are done within the FX100. It's not that you have to do that. You will receive the direct result of this calculation. So we are actually already at our practical presentation. I have here a FX100 on my desk, which is connected to an amplifier with a load of 4 ohm. The Flexus is controlled from a PC via USB, and on my PC I have the FX control software running. This software, by the way, comes along free of charge with every FX100 analyzer. So let me switch over to that software. I have started with creating a new empty project, and the first step I would do is here I would enter the hardware and wiring view just to add my virtual amplifier connected to my channel 1 input and output of the FX100, and then I can walk over to the worksheet. This hardware view is just very practical because it reminds me of the setup. This is a very simple setup, but in other occasions you have more complex settings, and with this hardware and wiring view you can make sure that, for instance, when you reload your project at a later time, you will remember how to connect the involved devices of your test setup. So let's swap over to the worksheets view, and now my first step would be I want to determine the output power of my amplifier. So I need the generator properties. I drag and drop them here on my worksheet. I unmute the output, and let's start with an output voltage of minus 10 dB volt, and our first step would be to measure the gain of our amplifier. And for that purpose I go here into the measurement tree, meter, and I select the gain of channel 1. I'm already ready to execute that measurement, run, and you can see here it's about 29 dB. Now let me enter this value into the corresponding panel so that the FX100, the instrument, knows about this information. So here I drag and drop the reference watt panel, and in here I adjust my load impedance as said before to 4 ohm, and I adjust the gain of my amplifier channel 1 to 29 dB. So now I'm already ready to enforce a certain output power to my amplifier. For instance, I could say I want to generate 50 watt. 50 watt shall be the enforced output power of my amplifier. And to verify whether this is actually happening, I will measure, because I have connected my amplifier also to the input of the FX100, I can measure the dissipated power in this panel. I just need to amend the unit to watt so that I directly will see the output power of my amplifier, which should be 50 watt. Let's see whether this is working. Correct, absolutely correct. So the FX100 has internally calculated the required output voltage to generate these 50 watt at the output of the amplifier. So in the next step, let's take a closer look at the behavior of our amplifier. And for that purpose, we activate here the step sweep, and we want to measure the linearity of the amplifier. And for that purpose, we have to change the step sweep mode to amplitude sweep. So this means we are generating a stepwise increasing output voltage of our FX100, which is the input voltage of the amplifier. And we're going to measure the output voltage of the amplifier and put this input voltage to the output voltage into correlation. And if this correlation is constant over different values, then we can see the linearity of our amplifier. So I need a step sweep measurement, the level measurement of channel 1. And in addition, I also want to take a look at the total harmonic distortion of my amplifier output. I start at minus 20 dB volt output voltage of the FX100, and let's increase the number of points to 50. That's fine, let's start. Let me briefly change the color of the THD result to red so that we can better differentiate it. Up here we have the level response, so the input voltage versus the output voltage. It's very linear up to -4, -3 dB. So in this range down here we have a very linear behavior of our amplifier. Up here apparently there is some clipping taking place, and you can see that down here as well. The distortion is jumping up heavily due to this clipping of the amplifier output. Now, by knowing this information, we could now change our test parameters. We could say we want to now execute this linearity test, but not with an output voltage, but to make sure that the amplifier output has a certain power, a certain watt. Let's say we want to sweep from 1 watt to 120. So this is actually the same principle that we did before. We enforce a certain output power of our amplifier. Now let's repeat the step sweep. This is basically the same what we did before, but now you see this curve has a kind of a bent shape. It's no more straight, and the reason is very simple. Here, down here, we have a linear unit, the watt, and here we have a logarithmic unit, the dB volt. So what we need to do, we have to change the scaling of the x-axis to logarithmic, and then we have again our nice straight line that shows the linear behavior of our amplifier. And the same down here, we change the x-axis to logarithmic scaling, and we have the same picture as before for the distortions. This feature here is pretty unique. There are not too many actually. We do not know any other analyzer that can do it, that can execute a step sweep based on a calculated, enforced output power of the amplifier. Well, in the next step, I would like to show you some more measurements to qualify the behavior of our amplifier. Let's now go over to the glide sweep mode. The glide sweep mode has the huge advantage that it is the fastest way to execute a comprehensive evaluation of the behavior of an amplifier. We would do basically the same measurements, which means level, and distortion, total harmonic distortion. And I guess you have noticed that this time I dragged and dropped these measurement panels from the glide sweep measurement tree. Now we need to adjust the bandwidth of our analyzer. We have the choice between 20 kilohertz and 80 kilohertz. I'm going to 80 kilohertz to get all the upper harmonics as well. The start frequency would be 20 Hertz, the stop frequency 20 kilohertz, that's fine. 2 seconds duration, okay. Now what we need to do first, we have to adjust the input range of our analyzer, and for this purpose we have this regulator. What is happening here? The FX100 will now execute this glide sweep, and it will measure the level of the input voltage, and then it will adapt the sensitivity of the analyzer, of the FX100 analyzer, to that expected input voltage. And that is important, that is necessary, because we cannot do that during the glide sweep, we have to do that in advance. So this is already our result. It is already taken over by the instrument. Again, level, frequency response, and here the distortion response. Let me color that red as before for better differentiation. So here you can see these results directly coming from a single step glide sweep. Now we would next try to we have measured this in dB volt, and our next step would be to express these two measurements in watt, because that is the topic of our presentation today. We want to measure these behavior, the level frequency response and the distortion response, in watt. This is how it looks like. Now here, when you take a look at the THD, you see some major distortions in the low frequency range, and then there's something happening up here which you cannot really take a close look at. So let me now change the y-axis scaling to logarithmic, and then we have a much better understanding of what is going up here in the upper frequencies. I had here a glide sweep of 2 seconds duration. I can go down to 1 second or even further down. So this is a very fast, very quick measurement with identical results. So here you have the opportunity to optimize your application, especially when you are in a situation where you have to save time as much as possible. For instance, in a mass production, you have to squeeze down the test time to the minimum. Here the glide sweep is probably the best choice for that. Well, let me go back to our presentation and summarize what we have shown to you. First of all, we adjusted the output voltage of the FX100 so that it creates a certain amplifier output power as given by us. Then I started with the measurements. First of all, the gain measurement of my amplifier in the meter mode. Then in the step sweep mode, we executed an amplitude sweep to determine the linearity of the amplifier, the output power versus the input level. And we also measured the distortion versus the output power. Then we executed a glide sweep level frequency response measurement expressed in watt, and the same as the distortion, so the distortion power, the dissipated distortion power versus frequency. Some hints and tips. First of all, if you execute such a test, you may have the demand to verify the result against a specification. Is it passed or is it failed? So you need tolerance limits. And I'm going to show you briefly how you could do that manually. There are actually 2 different ways of doing it. Manually, by editing these tolerance limits, as I will show you, or you can also record a couple of reference samples and then apply a headroom to the minimum and maximum or to the average. This is a little bit more complex, and we have explained that in a different webinar, so you can watch it there. Today, I just want to repeat the way how to establish a manually edited tolerance limit. I select the corresponding measurement graph. I click on Edit Data here in the properties. You see this is the same curve. And now I can very easily add some points at the places where I want to have them. And in this way, I can create a tolerance band so that the measurement curve has to be within that band in order to, this is one, in order to be accepted as a passed measurement. And the same goes, of course, for the lower points, for the lower tolerance limit. Okay, I could also edit these data numerically by selecting the Edit Data panel. Here we have the same points expressed as numerical values, so I can add more, I can amend them as I want, just for the sake of simplicity. I leave it as it is. I confirm, and now by repeating the measurement, you will see this is my tolerance band, the curve is within, and now you can also add a passed failed panel. I select the glide sweep level channel 1, and you see this was a passed measurement, so this shows you immediately whether this measurement result is within the given tolerances or not. Another hint, I showed you that as well. You may amend the scaling of our result graphs between linear and logarithmic so that you can always choose the one that fits best to your application, that gives you the most valuable information on a first view. And third hint, You can also overlay several measurements in one graph. For instance, you could measure level channel 1 and channel 2 and display them in the same graph panel, or you can also combine a level and a THD measurement in one graph. Let me briefly show you how to do that. I'm just deleting these two, and now I'm selecting my THD measurement and drag and drop it to this level graph. And you see down here I have this red curve that shows me that my THD result, so it's not very significant right now, but as soon as I would amend the y-axis scaling to logarithmic, you see here, up here, the frequency response as before, and below we see the distortion response, the red curve. Now you have both results in one single result graph. The prerequisite for that, of course, is that the y and the x-axis units are identical, so you can only plot results that are expressed, for instance, hertz versus watt, or hertz versus voltage, or dB volt, or watt versus volt, whatever. It has to be identical for the both measurements that you want to combine in one graph. Well, we're at the end of our presentation. Thank you very much for your attendance. Have a good time and see you soon again. Bye-bye.